Welcome to this video lecture on the subject transmission lines and antennas. So in this lecture we are going to discuss about waves between parallel planes. So first of all, what is a wave? A wave is a disturbance or change in equilibrium of one or more fields such that the field values oscillate repeatedly about a stable equilibrium. So basically there are two types, one is mechanical wave and electromagnetic wave. So electromagnetic waves are also known as EM waves produced when electric field comes in contact with the magnetic field. So they are the composition of oscillating electric and magnetic field. So there are solutions of Maxwell's equations which are the fundamental equations of electrodynamics. So we are going to consider the electromagnetic wave propagation between parallel planes. So here the direction of wave propagation is along the Z direction, and the boundary is taken as x equal to 0 and x equal to a in the parallel conducting plane. So we are going to apply Maxwell's equations for determining the electromagnetic field configuration in the region between the planes. So subject to appropriate boundary conditions, the Maxwell's equations are applied here. The del cross H equal to sigma plus j omega epsilon E. Sigma equal to 0 since the medium between the plane is air. So for the air medium the conductivity is 0. So sigma is 0. And next del cross H equal becomes j omega epsilon E, and del cross E equal to minus j omega mu H. So it is one of the Maxwell's equation. And the boundary conditions for perfectly conducting planes are E tangential equal to 0, H normal equal to 0. So applying wave equation, del squared E equal to gamma squared E, del squared H equal to gamma squared H. So where gamma is the propagation constant, so we're substituting sigma equal to 0, we get j omega square root of mu epsilon. So in rectangular coordinates and for non-conducting region, del cross H equal to minus j omega epsilon E. So del cross H is the curl equation. So it is the determinant matrix is written in the rectangular coordinates, and by substituting the E vector and we are equating the two terms of curl equation and electric field, we get these three equations. So this is an activity. And next, for del cross E minus j omega mu H, we apply the same curl equation and we get equations for relation between Ex, Ey and Ez. Here the propagation constant gamma equal to alpha plus j beta, where gamma is real if alpha have value and beta equal to 0. So it means there is no wave motion but only an exponential decrease in the amplitude. And if gamma is imaginary, alpha equal to 0 and beta have the value, it represents the wave propagation but no attenuation. And the other assumptions are, in the y direction the field is uniform and constant, so dou by dou y equal to 0, and in x direction the certain boundary must met, so dou by dou x there is no change, and in z direction the wave is assumed to propagate. So these are the conditions. So dou by dou z equal to minus gamma, then dou squared by dou z squared is written as gamma squared. So by substituting these assumptions, the previous 6 equations are modified as given this. And solving the equations, we get Ex equal to gamma by H squared, dou Ez by dou x, and Hy, Ey and Hx. So these are the 4 components of electromagnetic wave propagation between the parallel planes. So in equations 12 and 13 in previous slide, there is a component of electric field in the direction of propagation but no component of magnetic field. So these waves are known as E waves or transverse magnetic waves. And the remaining equation, there is a component of magnetic field along the direction of propagation but no component of electric field. So these waves are known as H waves or transverse electric waves. So assessment question, what is the direction of electric and magnetic fields of an electromagnetic wave assumed to propagate in the y direction? So these are the references. Thank you for listening this lecture.